So let's get started. Today we are going to study new chapter, which is chapter number 7, internal forces. Last time we discussed chapter number 5, the equations of equilibrium. We managed to calculate the reactions in a rigid body. So now today we are going to build on the what we had got in chapter 5. So today we are going to learn how to evaluate the internal loading which is going to develop in any structural or mechanical members. So for example, here we have a cantilever and we have force applied to this cantilever. And in order to design that beam here, we need to make sure that any point can take the load. And we know that we are going to find variation. So the loads at that point is not going to be similar to that point. But as a designer, I need to make sure that the material here can resist the loading at all the points. So I need to make sure that the material that I'm going to use is going to resist the loading. So in order to do that, I need to know the internal loading inside the structure. So for example, I need to know the internal forces in that section AA. So in order to do that, I need to take a section. I need to pass imaginary line. I'm going to call it section AA here. Then I'm going to know how to calculate the internal forces. And that is why we are going to got a method which is called method of section, because we are going to pass a section to the desirable point or the point in interest. So how we are going to do that? We are going to use the method of sections, because we are going to take a section into the point of interest. For example, here we have a simply supported beam. Here I have a ruler, and here I have a pin, and I have a system of loads. Then in order to know the internal forces, we need to take a section at the point of interest. Assume that I need to know the internal forces at the middle of the beam. So I'm gonna first I'm going to draw the free body diagram. We already discussed how to draw the free body diagram. Here we have the reactions. Here we have a pin. We have reaction in X, and we have reaction in Y. Here we have a ruler. We have reaction in Y only. Then, like I said, we call this method of sections. I'm going to pass a section here. Of course, it's an imaginary section at the point of interest. So here I need to know the internal forces exactly at the middle of the simple supported beam. So I'm going to pass the vertical line here, section here. Then what will happen? If I'm going to cut the beam at the middle, I'm going to have two parts. I have part AC, this part here, the left part, and I'm going to have the right part. So here is the left part, and here is the right part. Then, if you are going to cut the section here, and you are going to be like that, then this part is going to go down or go up or is going to move. So in order to know the internal forces there, I need to prevent the translation into X and into Y. Also, I need to prevent the rotation so that this part is going to be in equilibrium. So I'm going to compensate for the cut here by putting internal forces. So I'm going to have force perpendicular to the section and other force tangent to the section, and I'm going to have couple moment. Those forces is going to compensate for the internal forces here. The other part, in the right hand side here, the right part, also we are going to get the same thing. We are going to get a force here perpendicular to the section, other force here tangent to the section, and a couple moment. So those forces are responsible for the equilibrium of that part. So the material here is going to develop those forces in order to have safe design. If the internal forces more than the ability of the material, then failure will take place. So that is why it's important to know the internal forces, because we need to use a material that can resist those internal forces. So we are going to give them names, okay? We are going to have normal or axial force, this one in here. So since the point is C, we are going to have a force NC. And the normal or the axial force is going to be perpendicular to the section. So here we have the section. The force is going to be perpendicular. We are going to call it the normal or the axial force. We have other component which is tangent to the section. We are going to call this shear force, V. So here we have VC, and here we have NC. And finally, we are going to have bending moment. Here we have a couple moment. So we are going to call this bending moment. So we have normal force, NC. We have shear force, VC, and we have bending moment, MC. Of course, similarly, at the right part, we are going to have VC and NC and MC. Like you can notice here, we have NC, and here we have also NC, and they are opposite. The same goes for VC and MC, because those forces acting on the same point. So according to Newton's third law, these forces should be equal and opposite. And the next question is how I'm going to calculate these forces. Like I said, in order to have a safe design, the part now after the cut should be in equilibrium. So if you are going to apply the equation of equilibrium for that part alone here, we are going to be able to calculate NC, NV, and MC. Or you can use also the equations of equilibrium to the right part. So since those forces is going to bring the equilibrium here for that part, so I can apply the equations of equilibrium in order to calculate VC, NC, and MC. So those forces can be determined by applying the equation of equilibrium to the free body diagram of either section. So you can use this section or that section in order to know the internal forces here. So again, it's important to know the internal forces at that point here, so that as a designer, I will use a material and a section that can be more than the internal forces, so that I'm going to have a safe design. Then also you can ask me about the direction. Why you choose that direction and that direction and that direction? Well, we are going to use our own sign convention. So of course, here you can use whatever direction that you want. You can use random direction, but we have a widely accepted sign convention. So most of the textbook, they are going to use a certain kind of sign convention, and we are going to follow that path. So first, regarding the normal force, that force here, we are going to assume that the positive is going to create tension. So here, if I have the material, and if the normal force, like you can see here, is going to create tension. So if the normal force is going to create tension, then the force is going to be positive. So if here I have a tension, if I have a cut here, then the force is going to be opposite to that direction, and the force here is going to be opposite to that direction. So if you are going to have a cut, you are going to work from left to right. So the positive is going to be like that, and the negative is going to be like that. If you are working from the right to the left, the positive is going to be like that. And regarding the shear force, this one here, the shear force, the force which is tangent to the section, we are going to assume that if I have a material like that, and the force is like that and like that, and you are going to have a moment which is rotate clockwise. In that case, here we are going to say that we have positive shear. So if you are going to cut here, in order to bring equilibrium, this one here is going to be down, and this one here is going to be up. So here is the positive shear sign convention. And finally, for the moment, we are going to say that a positive bending moment will tend to bend the segment concave upward manner. So again, if you are going to cut here, in order to bring equilibrium, the moment is going to be like that, and the moment to be like that. So in order to sum up, we are going to say that if you are going to pass a section at a structure here, then if you are going to if you are going to take the left part, then the positive is going to be like that regarding the normal force, and the V is going to be down regarding the shear force, and the bending moment is going to be counterclockwise. If you are going to take the right part, you are going to have opposite direction, like we mentioned in the beginning of the lecture. Then if you are going to work in 3D, if you are going to deal with the left part, then we are going to have shear in Z. We are going to have shear in X. This one is going to be the positive. This one is going to be the positive. And here we have the normal force is going to be positive in this direction. And we are going to have a torsional moment here about Y, and a moment about Z, and moment about X. So if you are going to solve a problem in 3D, and you are going to take the left part, in that case, those are the positive senses. If you are going to work in 2D, you are going to take the left part, then those represent the positive senses. Like we said, again, you can use random senses, but those are the most accepted positive senses. And here in this course, we are going to unify our work. So all of us will going to stick to those sign convention. So now we need to learn the steps in order to calculate the internal forces. So we have like 3 steps. The first step, we are going to determine the support reactions. And in order to do that, first we need to draw the free body diagram, and apply the equations of equilibrium. And we learn how to do that in chapter 5. So I'm going to assume that no one is going to have a problem with step 1. Then in step 2, we are going to pass a vertical section. So the question is going to be like calculate the internal forces at a certain point. Then I'm going to pass a vertical section at the desirable point. And then I'm going to show all the internal forces using the sign convention like I just mentioned in the previous slide. And then you are going to have isolated parts. You are going to take either the left part or the right part. Then in order to know the values of N, V, and M, I'm going to select either the left part or the right part. Then I'm going to apply the equations of equilibrium for either the left part or the right part. We are going to say the summation of the forces in x-axis should equal 0. The forces in y-axis should equal 0. And the moment about any point in that part is going to equal 0. Then you are going to get a solution for the internal forces. So now let's start example so that we can have a better idea about how to determine the internal forces. So here we have example 1. In example 1, like you can see here, we have a beam. Here we have a rocker at A, which means that I'm going to have a reaction here, AY. Here we have pin support, which means that I'm going to get dy and dx. And the question here, we need to determine the normal force, shear force, and the bending moment. We need to calculate N, V, and M. And we have two parts for that problem. First, we need to calculate the N, V, and M at the point B, which is just to the left of 6 kilonewton. So we are going to cut here. Point B is the first part. Then we are going to make a section at the point C, just to the right of the force 6 kilonewton. So we have two parts for that problem. First, we need to know the internal forces before 6 kilonewtons here, and then we need to calculate the internal forces after the 6 kilonewtons. Also here we have couple moment at the point D. The dimensions are shown here. So now we are going to solve that problem. Like we said, the first step, we are going to determine the support reactions by using the free body diagram. So here is the free body diagram. Instead of the rocker, we have AY, and instead of the pin support, we have dy and dx. Here we have concentrated force, 6 kilonewtons, and here we have couple moment, 9 kilonewton meter. Now, like I said, we are going to use the equations of equilibrium, and you could say that summation of fx equals 0. You can start with that, or summation of fy equals 0. But we say that you can be smart about it. For example, here directly you can take the moment about the point D. So if you are going to take the moment about the point D, so dy is not going to cause a moment, dx is not going to cause a moment. So you are going to end up with only one unknown. And for that problem, he concentrated on AY because he are trying to use the left part. So if you are going to use the left part, it's enough to calculate AY only. If you are going to use the right part, if you calculate dy and dx, that is going to be enough. So in this example, since they are intended to use the left part for the solution, they only calculate ay. But normally, we are going to calculate dx. We are going to say that summation of fx equals 0. You are going to find out that dx is going to be 0. Also, we can find the value of dy by applying the equation summation of the forces about y-axis is going to equal 0, or you can take the moment about point A. So now we finish from the first step. We calculate the reaction AY. Then we are going to move to step number 2. We need to pass a vertical section at the point of interest. So here we have the free body diagram. We already know the value of AY. We are going to take a section here like required in the example. And that is a point B. So I'm going to cut here. And as a result, I'm going to have two segments. I have segment AB and I have segment BD. So regarding the segment AB, I need to show the normal force and the shear force and the bending moment diagram. Make sure that you are going to use the positive senses. We discussed this. This one is going to be the positive, and the positive. Also, we can use the right part. Also, again, we need to put the positive senses. Those senses here are positive to that ones here. So which one should I choose? Should I choose the left part or the right part? For me personally, I'm going to use the left part because it looks easier, and I already calculate the AY here. So now I'm going to choose that part in order to calculate the internal forces. So now in step 3, you need to take either left part or the right part. Of course, here we took the left part. Then we are going to apply the equation of the equilibrium for that part. So that part here is in equilibrium. We choose segment AB. So we are going to apply equations of equilibrium. We are going to say that the summation of the forces in x-axis equals 0. And here is the sign convention for that. Then let's look at the x-axis. We have only NB, which means that NB is 0. So now the normal forces came out to be 0. Then we are going to apply the second equation. Summation of the forces in y-axis should equal 0. Here is the sign convention. Now let's look at the forces acting on the y-axis. We have 5 kilonewtons, which is positive, and we have VB, which is negative. And we have this one here positive, and that one is negative. And the summation should equal 0, which means that VB is going to equal 5 kilonewtons. Now let's move to the last equation. We are going to take the moment about a point where I can calculate the MB. So I'm going to take the moment here at B. I'm going to take the moment about B. Again, do not forget the sign convention. All the forces that is going to cause a moment counterclockwise is going to be positive. So I'm going to take the moment here, which means that VB is not going to cause a moment, MB is not going to cause a moment. I'm going to end up with MB, which is positive, and 5 kilonewton. If I'm going to fix this one here and push from there, I'm going to have a clockwise moment. So this one times the perpendicular distance. Again, here is the line of action. Draw a point from the point of rotation. Draw perpendicular distance, shorter distance here. You are going to find out 3 is the perpendicular distance. So we are going to have minus 5 times 3 plus MB. So easily you can solve this problem, and the moment came out to be 15 kilonewton meter. So if you are going to take a section here, you are going to calculate MB and VB and MB. So in order to design that beam at that point B, you need to have a material that capable of handling those forces here. Otherwise, a failure will take place. Now let's move to part 2 of the problem. If you do remember in the problem here, we need to know the internal forces at B so that we got a suction here. And also we need to know the internal forces at the point C. So now we are going to take, we are going to pass a section here. So regarding the second part, we are going to take a section here at the point C. So now we are dealing with the segment EC. Again, we took the left part because we know the value of AY. Also, you can take that part, but that part, it look difficult. So always I'm going to look for the easiest part. And in that case, the easiest part is the left part. So we are going to show the internal forces. Again, we should follow the positive senses like we just learned. And the only difference between the segment AC and AB is the force 6 kilonewtons. So here we are going to have 6 kilonewton in the segment. Again, I'm going to say that the summation of the forces in X axis should equal 0, the sign convention. We are going to have 5 kilonewtons positive. We are going to get only NC regarding the X axis. So NC came out to be 0. Then we are going to apply summation of the forces about the Y axis should equal 0. Then look at the Y axis. We have 5 kilonewton positive. We have 6 kilonewtons negative. And we have VC negative as well. So I have 5 positive minus 6 negative, VC negative as well. And here we have only one unknown. So easily I can calculate the value of VC. Came out to be minus 1 kilonewton. And finally, I'm going to take the moment about the point C. Again, the sign convention is very important. 6 kilonewton is not going to cause any moment. VC as well. NC is not going to cause any moment. So I'm going to end up with only MC and 5 times 3. So this one is going to be positive. 5 kilonewton is going to cause negative moment. So I have 5 times 3 plus MC, and the moment came out to be 15 kilonewton meter. If you compare the segment AC and the segment AB, you are going to find the difference in the value of VC, the shear force, because here 6 kilonewtons is going to change the value of the shear. In the previous segment, the value came out to be 5. So before 6 kilonewton, we have shear force positive 5, but because of 6 kilonewton, like you can see here, I have 5, but this one is down. That is why here we end up with minus 1 kilonewton. So the only difference was in the shear force. Okay. So as a practice, in that problem, you can solve the problem using the right part. And in order to use the right part, you need to know the value of dx and the value of dy in the beginning, in the first step. So as a practice, to make sure that you understand the concept, try to use the right part, and you should end up with the same answer. Okay. So now I'm going to give you the chance in order to ask. Example 2 here, we have 2 members. We have AC and we have DC. So DC, it could be considered as a link, weightless link, in order to hold the beam AC. What we want here, we want to determine the internal forces acting on the point at the point B. So we need to know the internal forces at point B. So in order to do that, the first step need to be done. We need to calculate the reactions. In order to calculate the reactions, we need to draw the free body diagram. So in this example, again, we need to determine the internal forces at point B. The first step need to be done. We need to calculate the reaction for that beam here. So we need to determine the support reaction. We need to consider the free body diagram. So here at A, we have pin support. So instead of the pin support, we are going to have reaction in X and reaction in Y. So we are going to have AX and AY. And instead of the member DC, we are going to consider this as a weightless link here. So we are going to have a force reaction here in the same direction as the member DC. We are going to call it FDC here. And also we need to know how we are going to decompose that force. So here we have a proportional triangle. We have 5, 3, 4. So how did we get this? Like you can see here, the distance here is 8 and the distance here is 6. That means the distance here should be 10 feet. So here we have 8, here we have 6, and here we have 10. So we can use that triangle, that proportional triangle here, but he chose 3, 4, and 5 because 8 over 10 is the same as 4 over 5, and 6 over 10 is the same as 3 over 5. So if you are going to use this triangle or that triangle, it doesn't really matter. You are going to end up with the same result. So here we are going to use a 3, 4, 5 triangle. Then we need to, of course, decompose the forces. FD, you are going to have component into X and component into Y. Component into X is going to be FDC times 4 over 5. And the component in Y is going to be FDC times 3 over 5. And also here we have rectangular distributed loading. In order to deal with that, we need to express it as single resultant force. And we'll learn how to do that. We are going to get the area under the diagram here. So the height is 50 and the distance is 8. Then the resultant force is going to be 50 times 8, which is 400 pounds. So we got equivalent to that rectangular distributed load, which is 400 pounds, and it's going to be in the center like we learned. Then now we are in a position in order to use the equations of equilibrium. So those are the equations of equilibrium. Like I said, that you have to be smart about it in order to save time. So if you are going to use the first equation, summation of the forces in axis should equal 0. Like you can see here, you don't know the value of AX and you don't know the value of FDC. So this one is not going to work at that stage. If you are going to use summation of the forces in Y direction, also I have AY and I have FDC. I have two components, I have two unknowns, which mean that the equation cannot be solved. Then it's better to use the moment about any point should equal 0. So here I have two choices, either to take the moment about A or the moment about C. If I'm going to take the moment about A, I'm going to get the value of FDC. If I'm going to take the moment about C, I'm going to get the value of AY. So here I'm going to take the moment about the point A, which is here, which means that the AY and AX will not going to cause a moment. Here also that component FD times 4 over 5 is not going to cause the moment because the line of action is going to pass through the point of rotation. Then I'm going to have a moment because of FDC times 3 over 5. And if you are going to draw the line of action, then the perpendicular distance is going to be 8. And regarding the 400 pound, if you draw the line of action, the perpendicular distance will be 4 feet. So I have a moment because of this force and a moment because of that force. The direction of that one is going to be positive, and the direction of that one is going to be negative. So I have minus 400 times 4 plus FCD 3 over 5 times 8. Now I have one equation, one unknown. Easily I can solve for FDC. So FDC came out to be 333.3 pound. Now I can use summation of the forces in x-axis should equal 0. Then I have that one, and I already know FDC, which is that number. So if I'm going to apply that equation, I'm going to end up with only one unknown, which easily can be solved, and AX came out to be 262.7 pound. Now I can use the equation number 2, which is the summation of the forces in y-axis. Again, now I have the value of FD, which is that number here. So easily I can apply that formula. I'm going to have AY, which is unknown. I have, and it's going to be positive, 400, negative, and this value is going to be a positive. So I have positive, and negative. In that equation, I have only one unknown, which is AY. Easily I can solve for AY, and AY came out to be 200 pound. So now I managed to calculate the support reactions. Now I know the value of AX, I know the value of AY, and I know the value of FDC. Now I'm in position in order to calculate the internal forces. In step number 2, we are going to take a section. The section should pass about here, because it's required to calculate the internal forces at the point B. So I'm going to draw a section here. I'm going to draw the section here. I'm going to end up with left part and the right part. So in step number 2, we are going to pass a vertical section at the point of interest, which is here at the point B. I'm going to show the internal forces. I'm going to have segment AB and segment BC. So at segment AB, here I need to show the internal forces, the normal force, the shear force, and the bending moment. And again, do not forget the positive senses. Also, if you are going to use the segment BC, you need to put the normal force, the shear force, and the bending moment, and do not forget the positive senses. So a very important point here, it's worth mentioning. Remember when we were about to calculate the reactions here, we get equivalent to the rectangular distributed loading. So this one, we get equivalent single resultant, this one here. So then when you make a section, you need to deal with the rectangular distributed loading. So do not use the converted value. Do not use 400 pound. Okay, it's a common mistake. I've seen it a lot. So please, when you finish with the step number 1, do not use the resultant force as equivalent to that rectangular distributed loading. Okay, now we are going to cut here. I'm going to get the left part and right part. Then now you can convert the distributed loading for that part into a single resultant force. So here I have, like you can see here, I have 50 pound. So this one is the 50 pound. I need to multiply it by 4. So I'm going to have 200 pound. And the same concept is going to be applied here. This one is 50 pound per foot. I'm going to multiply it by 4 in order to get 200 pound. So do not use the equivalent resultant force from the reaction again here. So you need to use the equivalent after the cut. After you make the cut, then again you can make the equivalent force. Okay, do not forget to do that. So now I have two choices, either to take the left part or the right part. For me personally, I'm going to take the left part because here I have a force which is need to be resolved into x and into y. I don't want to do this. This one here is a straightforward. I'm going to choose the left part. So now we choose the segment AB, which is the left part. Of course, I need to show the positive senses here. Then I'm in position in order to apply the equations of equilibrium. So now I can use the equations of equilibrium for segment AB. I'm going to start with the summation of the forces in x-axis should equal 0. Again, do not forget the sign convention is very important. We are going to have MB, which is positive according to this. And I'm going, this force here, 262.7 pound, is going to be negative according to this. So this one is positive, this one is negative. The summation should equal 0. Easily I can solve for NB. So NB here came out to be 267 pound. So now I got the value of NB. Then I'm going to use the second equation, which is the summation of the forces in y-axis should equal 0. Again, do not forget the sign convention. Here we are going to have 200, which is positive. Here acting on A, the reaction actually, AY. Here I have the resultant force. We used to have the rectangular distributed loading. We converted to single resultant force, which is 200. So this one is going to be negative, and we have the BB is going to be negative as well. So I have 200 positive here, I have minus 200 negative here, and I have minus VB, which is here. One equation, when unknown, I can easily solve for VB. VB came out to be 0. So at that point, I don't have any shear force. Finally, I'm going to take the moment about the point B, which is here at the end of the section. Again, do not forget the sign convention. VB is not going to cause a moment, and B is not going to cause a moment. 262.7 also is not going to cause a moment. So here I have 200, it's going to cause a moment. It's going to be negative clockwise, and the perpendicular distance is 4. This one here is going to cause positive moment because the direction is clockwise, and the perpendicular distance is 2. And here I have a couple moment, which is MB. So I have positive, positive, and negative. So MB is positive, and I have this one here, it's negative, and the perpendicular distance is 4, and 200 here is going to be positive because it's going to rotate clockwise. Here is a point of rotation. If you push from here, you are going to end up with a counterclockwise moment. So here I have only one unknown, which is MB. I can easily solve for that equation. The moment came out to be 400 pound foot. So now I calculate MB, which is here. I calculated VB, which is here, and I evaluate the value of MB. Now that material should be able to handle all these internal forces. Otherwise, failure will going to take place. So that is why calculating the internal forces is very important process. So now I'm going to give you the chance in order to